In this recording, we will be discussing similarity measures. Similarity measures gauge whether a group of observations is similar or dissimilar to one another. Identify observations that are similar to each other or close neighbors in the K nearest neighbors. This technique will be discussed in one of the chapters later. Cluster analysis finds similarities among observations in the data and groups them into meaningful clusters based on similar characteristics. And we will be conducting cluster analysis also later. Clusters are formed in such a way that observations are similar within a group but dissimilar across groups. Similarity measures are based on the distance between pairwise observations, the records of the variables. Small distances implies high similarity. Large distances implies low similarities. In this example, we can clearly see that observations 1 and 2 are relatively close to each other, implying that they are similar to each other. We can see that observation 3 is dissimilar from the observations 1 and 2. So in this section, we are presenting a more formal way to measure similarities among observations for both numerical and categorical variables. The first measure we are going to discuss is Euclidean distance. And this is specific for numerical variables. So it's one of the most widely used measures for evaluating similarity with numerical variable. And it's defined, as you see, as the length of a straight line between two observations. It's technically the one that we have used in high school. If you have k variables, the Euclidean distance between the ith and jth observation is calculated like this way. The second technique that we are going to use is Manhattan distance. Manhattan distance is the shortest distance between two observations if you are only allowed to move horizontally or vertically. And this refers to the city of Manhattan, by the way. It's which is laid out in rectangular blocks. Manhattan distance between 2 points is the shortest path for a vehicle to travel from one point to another point in the city. And how can we calculate this? Using this formula. Example. We have 3 observations and we would like to find the Euclidean distance and the Manhattan distance. Just plug in the points into the equation, calculate the distance between observation 1 and 2. We get the distance between them, straight line. Do the same thing with observation 1 and 3. You get 7.62. 2, 3, we get 7.21. So we can see that the observations 1 and 2 are the most similar with the shortest distance of 1.41. Observation 1 and 3 are the most dissimilar given the longest Euclidean distance of 7.62. And we can see this in the plot. For the Manhattan, we just subtracting the points 1 and 2 from, this is the table again, this is x1, x2. So we subtract the values. Then we got 2. So the Manhattan distance between observation 1 and 2 is 2. 1 and 3 is 10. 2 and 3 is 10. So it's clear again, using Manhattan distance for the same set of observations, that 1 and 2 are the most similar based on the Manhattan distance. Observation 1 and 2 are now equally dissimilar to observation 3, because these are 10, right? For data with multiple variables with different scales, the scale of each variable can influence the distance measures. The different scales can distort the true distance between points and lead to an inaccurate results. For example, when comparing the customer information, data such as annual income tend to have a greater scale than the number of hours spent online per week, simply by the fact that the annual incomes are larger numbers. As a result, annual income will have a greater influence on the similarity measure than the number of hours spent online per week. So this difference in scale distorts the true distance between observations and can lead to an inaccurate results. So what to do? It's common to make the observations unit-free. How to make it unit-free? By standardizing or normalizing numerical observations before calculating the similarity measure for the data mining techniques. These transformations of numerical observations ensure that each variable receives an equal weight when the similarity measure is calculated. One common way we standardize numerical observations is to calculate the z-score, the one that it's the same z-score we took in statistics 1. What is the z-score? It measures the distance of given observation from the sample mean in terms of standard deviations. And we can calculate the z-value for any observation using this formula. It's the observation value minus the mean divided by standard deviation. Another widely used transformation method is min-max normalization. So what we do in this case, we subtract the minimum value from the observation and we divide the difference by the range, which is the max minus the minimum. This approach rescales each value to a number between 0 and 1. This is an example. You have the income, you have the hours spent, and what we found standardized value for both, the z value for the income, the z value for the hours spent. Also, we found the normalized income and normalized hour spent. For example, if you look at Jane's here, the standardized income is 1.247. So it's 1.247 standard deviations above the average income for all of the customers in this sample. However, Kevin is negative, it's 1.189 standard deviations below the average income. If you look at the normalized income, because the normalized rescale the variable from 0 to 1, Jane has the highest income, Kevin has the lowest income, right? Euclidean and Manhattan distance measures are suitable for numerical measures. When dealing with categorical variables now, we rely on other measures of similarity. For example, you may be interested in analyzing types of cars, where the categories of the categorical variables include sedan, sport utility, truck, minivan, etc. And recall that categorical variable with only two categories, we call it binary variable. So when analyzing loans, the categories of the binary variable include approved or not approved. And the two commonly measures that we're going to use to study the similarity measures for the categorical variable, the first one we call it matching coefficient, and the other one we call it Jacquard's coefficients. What is the matching coefficient? Matching coefficient for a categorical variable is based on matching outcomes to determine the similarity among observations or records. So the matching coefficient between any two observations calculated using this formula, number of variables with matching outcomes divided by the total number of variables. The higher the value of the matching coefficient, the more similar the two observations are. A matching coefficient value of 1 implies a perfect match. So this is a list of college students. Each record shows the student's major, field, sex, and whether or not the student is on the dean's list. So the question says, let's compute the matching coefficient between all pairs of the students and determine how similar or dissimilar they are from each other. So after finding the matching coefficients, we got 1 over 4, which is 0.25, between 1 and 2, between 1 and 3, it's 2 over 4, between 2 and 3 is 0 over 4. Because what is the formula again? The formula says number of variables with matching outcomes divided by total number of variables. For instance, number 1 and 2, look at them. These are dissimilar, these are dissimilar, and these are dissimilar. These are similar. So it's 1 out of 4. 1 and 3, business, this is 1. MIS accounting, 0, nothing. Female, this is 2. Yes or no? No. So we have 2 out of 4. 2 and 3, they are dissimilar, right? So based on matching coefficients for these 3, we can say that students 1 and 3 are the most similar to each other, whereas students 2 and 3 are the most dissimilar. The matching coefficients makes no distinction between positive outcomes, like made a purchase, and negative outcomes, did not make a purchase. Therefore, may provide a misleading measure of similarity. For example, consumer purchasing behavior at a grocery store where thousands of products are available. Two customers purchasing the same product exhibit similar behavior. However, if one customer purchases only a cupcake and the other purchases only organic apples, most people would conclude that these two customers are not similar. However, a simple matching coefficient would account for the fact that neither of the customers purchased thousands of other products that are available, and therefore produce a very high value of matching coefficients. So that's why we need another measure to do matching, which is called Jacquard's coefficient. It's more appropriate to measure of the similarity in situations where negative outcomes are not as important as positive between any two observations. So how to do this? We just take the number of variables with matching positive outcomes, then we divide this by the total number of variables minus number of variables with matching negative outcomes. And this is an example. A retail store collects points of sales information that shows whether or not 5 products were included in each sales transaction. A yes indicates a positive outcome, while no indicates a negative outcome. So the yes is the positive, no is the negative. Transaction 1 indicates that a customer purchased a computer, keyboard, mouse, headphone, for example. So compute and compare matching coefficients and Jacquard's coefficient for all sets of pair transactions. We just apply the formula, and we just count the positives, count the negatives, count the total, then we subtract. We apply the formulas, then we get all of these numbers. So if you can see that this shows the measures produce the highest coefficient for transactions 1 and 2, implying that these transactions are the most similar.